So today's lecture, we continue with our power series. So Taylor series, our power series. Now 6.3 is actually a chapter, that the section we already looked at, and was called almost like that, right? It was called Taylor polynomial. So now we're saying we say Taylor series. You could try to guess what is going on here, right? What was Taylor polynomial as well? We would do this, calculate this nice table, and then of degree 5, we would stop at degree 5 and write down what the polynomial. And what we're going to do today is exactly the same, except we're not going to stop. Now, of course, that's not possible. We cannot really carry that out. But that's the idea. So let me review a little bit what Taylor polynomials were, and then immediately segue into what Taylor series are. And I'm going to do this on an example. Let's take the function ln of x and centered at c equals 1. Often we choose a center, especially when we try to do calculations, that is very well suited for this particular function that we deal with. And here, in this case, the ln of 1 is very easy to find. We know what it is. It's actually 0, right? So we could take different centers, and we will at some point, but you will see. Well, I said we will. No, we probably won't do that much, but it's possible to do that. Okay, so how did it work? So let's first start saying, okay, I want a Taylor polynomial of degree 4, say. So the degree 4 polynomial, Taylor polynomial, but we're eventually going to go to series. So, okay, so let's do that first. How did it work? We made this table, right? That was such a nice thing to do. It was easy. 0, 1, 2, 3, 4. So the first column was the derivatives of this function. So this is f, of course, yes. Okay. In the second one, we do this, whatever function we have in the first column, now we substitute at the center. So we use our center here, and this is, we put in the 1 here, okay? And then the last column was actually basically the same, except we also divided by n factorial, because that's another thing that came into the picture. Okay, so the function, the 0 derivative means just the function itself. That was ln x. So remember, how do you go from here to there, and then from there to there? That's always taking derivatives. Okay, so that's what we're going to do. Okay, I'm going to erase it again, that we don't get too much. Okay, so let's take derivatives. Derivative of ln x is 1 over x. Now we have to take derivative of that again. So let me write. And sometimes it's therefore easier to write it as with a power, because we're going to do the power rule. So it's minus x minus 2. Exponent comes down, subtract from 1 from exponent. We're taking derivatives, not antiderivatives, right? Okay. It's true that it's easier to now take the derivative the next time, but on the other hand, I'm going to have to plug in, and then for plugging in, it's easier to write it as a positive exponent. So you see why in 1275, so why were they always telling you have to simplify and this and that? It's not really true that you always have to simplify. It really depends on what you want to do. If you take derivatives, you want to write negative exponent. If you want to plug in, you want positive exponents. Okay, so next one. We take the derivative of that one with the power rule. Negative times negative 2, that's 2x to the negative 3, which, if we write it down in powers again, is 2 over x to the cube. And one more time, minus 6x to the minus 4, which would be minus 6x to the 4th. Okay, now we plug in 1. The ln of 1 we said is 0. So from, let me make again a picture. So from here to there, what we do is put x equal to 1. That's the only thing we do at each row, in each row. Okay, 1 over x, plug in 1, that's 1. 1 over x, minus 1 over x squared, plug in 1, negative 1. Any power of 1 is 1, so. Then we get 2, and then we get negative 6. Good. Finally, we have to divide by n factorial. Now, 0 factorial and 1 factorial are just 1, so we don't do anything. 2 factorial is minus a half, so this is 2 factorial is a half, right? 3 factorial is 6, so we get 2 divided by 6, which is 1/3. And 4 factorial is 24. So we get minus 6 divided by 24 is minus 1/4. Okay? Perhaps let's do one more. No, let me write down what P4 is. Okay, so P4 therefore is, I'm going to write P4 here. P4 is going to be, remember, these are now the coefficients of the powers of x minus 1. Why x minus 1? Because x minus the center, okay? So that will be 0 times x, the constant, so that's just 0. I'm not going to write that. 1 times, again, I'm not going to write it, so x minus 1. So remember, centered at x equals 1 means it's in terms of powers of x minus 1, right? So we get here various powers of x minus 1. Okay, so here this is the first power, then the second power has a coefficient minus a half. So minus a half x minus 1 squared. Then we have 1/3 x minus 1 cube. And then the minus 1/4 x to minus 1 to the 4th. You kind of see a pattern already, but just to see that we can figure out a little bit more, let's go one further. We take the derivative of this guy, that is, no, here that's easier to do there. That's 24x to the negative 5th. So plug in 1, we get 24, and now divide by 5 factorial, which is 120. That's actually, amazingly, it's just 1/5. Well, if you kind of see what happens, it's not so amazing. So the next one is 1/5 x to the minus 1/5. Of course, now we are calculating P5. But I think you kind of see the pattern, right? What you get here? 1, minus a half, 1/3, minus 1/4, 1/5. So it's the reciprocals, but with an alternating sign. If you want, it's kind of, it looks like the alternating series, right? But of course, it's a power series in x minus 1. So we could easily write down what P6 is, right? What would be P6 be? Well, we have to add one term. That will be 1/6, but I have to change the sign, so alternating sign, so this would be it. So this would be P6. And now I can write down what P7 is, right? Okay, that now again at the plus, x minus 1 to the 7th. So you see here that I can kind of write dot, dot, dot. And therefore I get, we could call this P infinity. And this is what we call the Taylor series. So the Taylor series is basically you keep calculating this table here, but you never stop. So you go all the way to infinity, which is of course not possible, but we see that once we recognize patterns, we can, right? So that's what we have found now. So this is the Taylor series of ln x. But what does that now actually mean? Okay, that's a little bit more subtle in general, but this is Calc 2. It's just, believe me, it's only just baby calculus that we're doing. Although you might think it's a very difficult course, which it is, of course, but there's still a lot of the things to do. But for us, therefore, what is going to happen is actually very simple. Namely, whatever function that we will work with, when you find its Taylor series, the function is going to be equal to it. Well, that cannot be, because power series, we know, have radius of convergence. So I'm going to write this up here. In this particular case, what we have is, we get this series. I'm going to write it out first by writing out a couple of the first few terms. I'm just copying this above here, but just as, so dot, 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 okay? But, okay? This equality is only for the radius of convergence, only at the, or perhaps even better, at the interval of convergence. Okay? Now, we are not really going to do this for arbitrary functions. We do it for Taylor polynomials. That's going to be definitely a problem again on one of our final exams or tests and so on, but we are not going to do this for arbitrary functions. So what I'm now going to do is something you actually never will have to do, but I just want to show you that what I'm doing, how do I get to these results? Okay, I'll tell you shortly what it is that we will actually do. It's not that we, of course, we're going to do things here in this section, but not everything that's done in the book we will look at. So now I want to calculate the interval of convergence. And what is the problem if I write a series like dot, dot, dot? Well, in the for the interval of convergence, I have to use the ratio test, so I have to know what an is. So I kind of need to know not just dot, 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 I really need to write this in the summation sign. And that's the reason why we work with these sigma signs, because this allows us to write down, so this here will be this an, and then it will be x minus 1 to the power n, right? So the question is, what is this number? Why do I start from 1? Well, you see, because there was no 0 power here, right? So that's why I only have to write 1 here. So what is the an? Okay, it's not so hard to see, right? Because look at the numbers, 1 minus a half, 1/3. It's very easy to write that down. It's 1 over n, but alternating. It really is just there, the alternating sequence that you would have. So that's our an. So this is how we write down, sorry, it got a little bit, okay, let me put everything on the same level here. It got a little bit screwed. Okay, x minus 1 to the power n. So now we have a formula, and so we can do the ratio test. So what I'm saying, so I'm going to do the ratio test, but I said this is not something we will have to do all the time. So I'm just going to show you, nonetheless, how it works. After all, there's going to be a test on the ratio. We're going to be testing the interval of convergence, so you want to definitely see how these things go. Okay, so in the, for the ratio test, for the radius of convergence, or rather the interval of convergence, what we have to do is take this limit. We have an here, and then on top we do the same, but with a higher index. So let's see. We have here, first of all, the absolute value. Okay, no, let me write it still. Let's take our time. So this is what we would get if we plug in an, and so an plus 1 would be the same thing, but everywhere n is now replaced by n plus 1. Make sure that you understand how this works, right? Some people start changing x's and stuff, but no, it's only the n's that becomes n plus 1s. And there's absolute values. Now, about the absolute values, there are two things that happen, right? There's this negative sign, which, if we take absolute value, is gone. So let's do that already. Okay, I'll do it with, I'll show you that I've done how it comes. So I said, okay, I don't care about this, okay? But there's also x minus 1, right? That could be negative. Okay, so let's now rewrite everything. I get the limit for n going to infinity. But I mean to say, right, let's write our fraction in a single fraction, not a compound fraction. So we have, what do we have here? The n plus, okay, so n plus 1 is in the bottom, and the n is on top. This n goes on top, right? And then we have here absolute value of x minus 1 to the power n. This is where the absolute value has to stay. And x minus 1 to the power n plus 1. And then exponents cancel here, so this whole thing cancels, and we have an exponent 1 left. So I get x minus 1, and then, sorry, the limit for n going to infinity, n over n plus 1. Can I just say this is 1? Is everybody clear that this limit is 1? Okay. Okay, now I'll show you, because I want you to do it anyway. So if you have to do it, I have to do it too, right? So divide by the highest degree term, and then you get x minus 1, and then you get limit n going to infinity 1 over 1 plus 1 over n. And now I can say this guy goes to 0, and so the whole thing is, as I said, just 1. So x minus 1. Now remember, let me write this a bit more carefully, x minus 1. Now remember, we are doing the ratio test, and this says that whatever you get has to be less than 1 for convergence. So this is a condition. And then how do you find the radius of convergence? The radius of convergence is you solve for x minus 1, and then this number is the radius of convergence. So in this case, it's just 1. And what does this mean? That means you take the center. Now be careful. What was the center? The center was 1, right? We had the center 1. So what we need to do is, here is 1, and then we can go 1 that way, that would be 2, and 1 that way, that would be 0. So the interval of convergence, therefore, is in between these two here. Oh, no, I'm going to agree. This whole thing. Now, what about the endpoints? Well, when we deal with Taylor series, we are actually not really going to care about that. So we don't really know. So we don't know, and we don't really care. But you could look at it, and you will see that in one endpoint it's not, and the other one it's I think it's no. Wait, what is it now? So if I plug in x equal 0, yeah, then you get so now. If I plug in x equals 0 in this thing, then you see the series becomes just the alternating series, the harmonic series. If I plug in x equals 2, then you get here a 1 to the power n, so you get the alternating harmonic series, which is convergent. So the actual thing is, I can be more precise, but we're not going to do that. So this means this. What does this now all mean? This means that this function ln x, of which we took the Taylor series, and the Taylor series we figured was of this form, is equal to each other for x less than 1, exactly within this interval. What am I saying here? I say it wrong, right? For x in the interval between 0 and 2. Sorry. For x between 0 and 2. Or another way of saying that is if the absolute value of x minus 1 is less than 1. Which was the original condition here, right? I can say it that way. Sometimes people say it this way. Sometimes people want to really see what x itself is, and you do this. Okay, they mean the same. So that's what a Taylor series of a function is. So in principle, I can write down any function and tell you, okay, given the center, find the Taylor series. The problem is that you need, as I said, to know the radius of convergence, you need to see the pattern here. You need a formula like this. And how are you going to do that if the pattern is very complicated? And which it invariably will be if you take anything more complicated than a simple function like ln x and so on. So therefore, as I said, we're not going to do the method this way. And next time I will tell you how we will do it. So today I want to just give one or two more examples here. So let's do this now for f of x is the sine of x. Okay, and the center here will be 0, because, again, the sine of 0 is something I know what it is. Okay, so I'm going to start a table again. We have done this several times, I think, for the sine of x, but just let me make my table a little bit bigger. Okay, so I'm not going to do too many cases here. 0, 1, 2, 3, perhaps. Oh, yeah, I said that, but then I realized you'll see why I actually have to do a few more. Okay, the sine of x, or f of, oh, sorry, no, there's no sine of x that comes here. It's f to the nth derivative of sine of x. Here we get the nth derivative of sine of x. You evaluate at 0, and then finally you divide by n factorial. Okay, so we start with sine of x, derivative is cosine of x, derivative of that is minus sine of x, so just be careful with the minus signs. Then minus cosine x, derivative of minus cosine x is minus sine of x, so sine of x, and the cycle starts over. We know that this is this kind of repetitive pattern. If I plug in 0, the sine of 0 is 0, and the cosine of 0 is 1. So we get a 1 here, a 0 here. Now we get negative 1, 0, 1. Finally, we have to divide by, well, 2. Divide by 2, there's nothing happened. Now we have to divide by 3 factorial, which is 6. Okay, that's 6. There's nothing I can do with that. 0 again, and now we have to divide by 1 over 5 factorial. So actually, I prefer to write this just as 1 over 3 factorial, and then this as just 1 over 5 factorial. So what do we see? What can we guess? Certain things. I think let's write down what the series is. Right? These are the coefficients. So our P5. Let's start just writing the polynomial degree 5. What would it be? These are the coefficients of the powers of what? X now, right? Because we are center 0, x minus 0. Okay. So the first coefficient is 0. The next one is 1, so we get just an x. Then we have no square, okay? And then we have minus 1 x cubed. And then there's again no fourth power, so the only next thing is the fifth power. Okay? And you kind of, factorial, I forgot my factorials. You kind of see what's happening, right? So you see there seem to be only out powers. There also seems to be a chain of sign, 1 plus, minus, plus, and we should have gone to the 7th one to see that actually is a minus there. And also, if it's something survives, it's this factorial in the denominator, right? It's either 0 or this factorial in the denominator. And that's really what it is. So we can do we could calculate a little bit more, and therefore we can actually kind of guess what it looks like. But now to find the radius of convergence, you have to write down a formula for the general term, and that gets already a bit tricky. And so I prefer not to do it, okay? And I'm going to just tell you what the radius of convergence is. The radius of convergence is infinity. Now, you could try it yourself if you want to do that. It's, as I said, the problem is a little bit that to find a good formula, right? And there's another problem is that the formula, well, it's actually only going to be, it's a little bit weird because we're going to work with only odd powers, okay? Now, what is this? So let's put this now aside. As I told you before, we're not going to do it anyway, so we can accept it here that this is the right answer. And the meaning of this therefore is that the sine of x, the function where we started with, is equal to its Taylor series for all x's less than infinity. Yeah, but that's everything, right? So for all x, that's what infinite radius of infinity means. You can go as far as you want, you keep being convergent. That's kind of surprising, right? You have a function, nice function, sine of x, that you can now write everywhere. We remember we were in the previous, in 6.2, we did see some functions that are equal to power series, but that was for limited domains, right? It was for x less than, well, whatever. It always came from the geometric series, which had an actual really interval-loving convergence. But this function is actually, it doesn't matter what you plug in. It's kind of surprising because, I mean, there are big numbers, you know. If I put in a zillion here, why is the sine of a zillion the same, well, plugging it in this way or plugging it in that way? And remember, the sine is a function that goes up and down, right? The sine looks like this. But do you see that this function is the same, has this is periodic? It's not clear at all, right? So it's kind of surprising. Okay, so that's what Taylor series are about. Now, the one thing I wanted to now say is how we're going to use this in the next section. So today's rather, we're not going to cover that many material, I mean. But I want you to tell you already this is what we will be using. This is a table 6.1 on page, well, I don't know where I get the page number on my, well, in 6.4. Be careful, the table number is 6, but it's in 6.4. Now, it's not even the entire table that I want you to know, so that's why I want to make the table. So we will use the following table. I'm going to put it that way, meaning to say, whenever it comes to finding a Taylor series, if it's one of the ones in the table, we just copy it. So we're using the table here. And so on the tests and exams, you look at the table and say, oh, there it is. Now, I have to warn you, the table in the book is not as nice as you might have wanted to. So I'm going to make it a little bit nicer. So we have here the function. And then here we will write the Taylor series. Now, a bit about terminology before I write this down. This is called Taylor series, but it's also called Maclaurin series. Now, Maclaurin is also a mathematician, as is Taylor, and they kind of simultaneously worked on this thing. So to honor both, they give a name to these series. So in general, we call it Taylor series, but Maclaurin series means that the center is 0. That's, some people use it at that. Honestly, when I have seen it in higher level courses, when everybody calls it just Taylor series, no matter whether the center is 0 or not. So be aware that the book uses these two terms, but I'm going to ignore that. So here I'm going to write the Taylor series. And then finally, I'm going to write the radius of convergence. In the book, they give the interval of convergence. Again, I'm not going to be interested in that. The first function is something we did last time, 1 minus x. That was exactly the geometric series, so that was 1 plus x squared plus x cubed plus dot, dot, dot. And the radius of convergence, I hope you remember, it was 1. right? So R was 1 here. In other words, everything of absolute value x less than 1. Okay, so yes, sorry, the center is always 0. I said the book calls this Maclaurin, writes in the table Maclaurin series in this here, but that is because we will always work at center 0. Sorry. Well, perhaps, okay, sorry. It's actually not true. There's one exception, so let me not even say that. So then actually I'm making a better table than the book. So remember, later on, if you want to study this material, this is where the table is, okay? So make a note of yourself, oh, if I need to see this table, this is where you can find it. Okay, let's do sine of x, which we just had done, right? And there we saw it was the powers of, that's here, you see, it were the odd powers of x. So we had x, and then minus 1 3 factorial x cubed, plus 1 5 factorial x to the 5th. The next one will be a negative 1. In the denominator would be 7 factorial, and the power x to the 7, and so on. And here the radius of convergence was infinity. Now, it should not surprise you that the cosine must be very similar in nature. And what happens is, instead of odd powers, you're going to have the even powers. So you get 1, then minus 1 over 2 factorial x squared, plus 1 over 4 factorial x to the 4th, minus 1 over 6 factorial x to the 6th, plus so on. And of course, this is also infinite radius of conversion. In other words, these two, this series and this function, are always the same. You might say, why is this a 1 then? Well, what would it be? It would actually be 1 over 0 factorial, but that is 1, right? If you follow the pattern. Okay. Okay, so that's the two trig functions. Another one that we always, in the beginning, when we did Taylor polynomials, we discussed was e to the x. Because the derivatives are extremely simple there. And what we get is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial. You see the pattern, right? It's, again, factorials in the denominator, and but now no alternation of sign and everything. And look how nice this is. Again, this is infinite. Okay. Then the only other one, there's more in the book, but the only other one that I'm interested in is the ln of x that we just did. So let me write down this ln of x here, right? But you see the center is 1 here. So these are center 0, and this one, the ln of x, is at center 1. And that was x minus 1, let me see, I don't remember it by heart. Yeah, and then minus a half x minus 1 squared, that's how it went, yeah. Minus a half x minus 1 squared plus 1/3 x minus 1 cubed minus 1/4 x minus 1 to the 4th, dot, dot, dot. But r was 1 here. And remember, it's the center is 1, right? So that the interval is from 0 to 2. So these are basically our 5 functions, if you want, that we will, I'll put it nicely like this, and you can take a picture of it if you want a snapshot of it. Perhaps I should do that too. I don't know how to do that, so I'll think of it. Perhaps I can post it then. No, I'll let you figure it out yourself. But make the table yourself once in a while. It's good to write things down, then you know how it's easier to remember formulas if you actually write them down. Okay, what else do I want to say about this? That the book has a few more. In particular, one that the book has is about the arctangent. Now, that we actually know, because we did that, we solved that last time in 6.2. In the homework solution of 6.1 today. Sorry, it's in today's homework. It's one of these videos. Sorry, I make so many videos I don't know anymore what is what there. But it's in one of the videos where I find the series for arctangent. Okay. All right. That's all for now. And so next time we're going to work with them in the same way that we worked with the geometric series in 6.2, namely, what are the 3 things that we will be able to do? We can plug in, substitute, we can take derivatives, and we can take antiderivatives. So that will allow us to make new Taylor series starting, or power series starting from given ones. And therefore, it's very important to have this table handy, because we will always start with one of those. Remember, this was basically starting with this, was basically what we did in 6.2. Now, so 6.4 is going to be mostly working with these guys. Okay, so don't forget to leave a comment.